Welcome back to my Let's Play of Orbiter. This time I am finally going to be reading the Dragonfly Operations Handbook. And now this video will not be interesting. It will probably also go on a long time. So feel free if you want to skip it, but know that a lot of the stuff that's in this is basically a requirement for being able to operate the Dragonfly properly. I might do a video later of just summarizing things, or that might just be in unison with when I'm doing the full power-up of the Dragonfly. So without further ado, I will get started on this. Again, I'm sorry for the very boring video, but hopefully the Dragonfly, this will help those who have been having problems with the Dragonfly. So, Section 1, Electrical Power System. The electrical power system consists of the equipment and reactants that produce electrical power for distribution throughout the space vehicle, and fulfill all power requirements for the vessel. The EPS operates during all flight phases. For nominal operations, very little flight crew interaction is required by the EPS. The vessel has no primary hydraulic system, and thus all operating and motor power is electrical based. The EPS is functionally divided into three subsystems: power reactant storage and distribution, or PRSD, two fuel cell power plants, and one battery, and electrical power distribution and control, or EPDC. The two fuel cells generate all 28-volt direct current electrical power for the vehicle through an electrochemical reaction of hydrogen and oxygen. At the hydrogen electrode, or anode, hydrogen is oxidized according to the following reaction. H2 plus 2H2 plus 4OH negative turns into 4H2O plus 4E negative, forming water and releasing electrons. At the oxygen electrode, or cathode, oxygen is reduced in the presence of water. It forms hydroxyl ions according to the following relationship. O2 plus 2H2O turns into 4-hydroxyl. The net reaction consumes one oxygen molecule and two hydrogen atoms in the production of two water molecules, with electricity and heat formed as a byproduct of the reaction. The power reactant storage and distribution system stores the reactants, cryogenic hydrogen and oxygen, and supplies them to the two fuel cells that generate all electrical power for the vehicle during all mission phases. In addition, the subsystem supplies cryogenic oxygen to the environmental control and life support system, or ECLSS, for crew cabin pressurization. The hydrogen and oxygen are stored in three tanks at each at cryogenic temperatures, 170 Kelvin for liquid oxygen and 70 Kelvin for liquid nitrogen, and supercritical pressures above 1400 kPa for oxygen and above 2000 kPa for hydrogen. The system stores the reactant hydrogen and oxygen in a double-walled, thermally insulated spherical tanks with vacuum annals between the inner pressure vessel and the outer tank shell. Each tank has heaters to add energy to the reactants during depletion to control pressure. Each tank is capable of measuring quantity remaining. Power reactant storage and distribution. PRSD is controlled by switches located in the upper left corner and lower left corner of panel 1. The switches can direct the flow of cryogenic reactants and isolate parts of the PRSD tanks in case of leaks. The top row of switches control isolation valves for each of the three oxygen and hydrogen tanks, tank isol valve. When set to close, down, a DC-powered engine will mechanically close reactant access to PRSD. Typical setting is tanks 1 and 2 open, tank 3 isolated. Isolation motor operation is indicated by a talkback indicator above each switch. Talkback will show white when isolated motor is stopped and bar pole when motor is operating or is damaged. Typical closing time for an isol valve is about 3 seconds. Given that isol valve's operation is necessary in certain circumstances to start or restart the fuel cells, the power needed for motor operation is provided directly by battery rather than from a DC bus. Care must be taken that a minimum power capacity is stored in the battery to assure that isol valve functioning is in case of a fuel cell shutdown. Second row of switches controls cross-feed valves to the cryogenic manifold, or X-feed. Normal piping configuration is tank 1 supplying reactants to FC1, Tank 2 supplying reactants to FC2, and Tank 3 functioning as backup and ECLSS supply. By positioning the crossfeed switch 1 to open, tanks 1 and 3 will supply reactants to both FC1 and ECLSS. Positioning the crossfeed switch 2 to open, tanks 2 and 3 supply reactants to FC2 and ECLSS. Opening both crossfeed valves, tanks 1, 2, and 3 supply reactants to FC1, FC2, and ECLSS. The last two switches on the last row, react valve, control the reactant valves to the respective fuel cells. Same operating procedures apply as the tank isolation valves, with a closing time of about 3 seconds and a power supply from the ship's battery. Lower on the panel, two switches, cryo-isol valve, control isolation valves that separate PRSD manifolds from external vent valves. Additionally, in the case of O2, it separates flow from the cryogenic O2 manifold to the ECLSS systems. OVB dump valves represent a high capacity, up to 450 grams a second, overboard vent valve, for quick discharge of reactants in case of an emergency. OVB vent valves are safety overpressure valves that pneumatically open when the reactant pressure exceeds certain safety limits. In the case of O2, the safety overpressure valve will open at 1500 kPa and resettle at 1450 kPa. For H2, the overpressure valve will open at 250 kPa, or 2500 kPa, and resettle at 2450 kPa. For the H2O waste tank, the valve will open at 1000 kPa and resettle at 900 kPa. The two H2O vent valves are non-propulsive in that it will not affect the state vector of your ship. H2 and O2 valves, both dump and OVP, will impact a small propulsive negative y-axis force when discharging. The high-capacity dump valves might take up to 10 seconds for opening and closing. A talkback will indicate when the motor is operating. Additionally, an open-close indicator will permanently indicate the respective position of the dump valve. Power to the high-capacity dump valve motor is supplied by the battery and is not selectable by the crew. Tank heaters switches control electrical heaters that are located inside each cryogenic tank. Middle position, auto, will automatically turn the heaters on or off to maintain reactant pressure within operational limits. When the heaters are at auto pressure, or position, the heaters will automatically be turned on for every tank that reaches a minimum operational pressure of 450 kPa for both O2 and H2 tanks, and then turn off when the pressure reaches, again, 470 kPa. As the tanks are depleted, the tank heaters should be turned to the off position to save electrical power and to prevent overheating of the reactants. Basic fuel cell operations is based on super-cold reactants flowing through the FC stack for cooling purposes. Excessive heating of the reactants in order to maintain pressure means warmer reactants will enter the FC stack, which might lead to FC overheating. An overheated fuel cell will also produce warmer H2O as a byproduct, which in turn is used as general coolant throughout the ship to maintain a thermal balance. A higher H2O temperature in the H2O tank means warmer water will flow through the coolant loops, leading to a large number of problems. Tank heaters are powered by their own DC bus, HTRS bus, linked to DC1. Fuel cells and battery. In normal operation mode, only one fuel cell, FC1, is active, running on reactants supplied by tanks 1 and 2. In case of exceeding power loads only, or as a backup, fuel cell 2 might be started also. The two talkback indicators monitor proper reactant flow to the respective fuel cell. The talkback will indicate white at normal flow and bar pole if flow is less than nominal. The start-stop switch controls power from the battery to reactants pumps that direct O2 and H2 flow to the respective reactant plates inside the FC stack. The start switch must be held in the start position the start momentarily position for approximately 15 to 20 seconds until the fuel cell chemical reactions can supply enough power to the fuel pumps for self-sustainability, which is indicated when the two reactant talkbacks turning white. The second purge norm switch will trigger the automatic purge sequence for the respective fuel cell. When set to purge, the pumps will direct as much as 900 grams per minute of reactants into the fuel cell, for the high volume of reactants to clean the fuel cell stack from diverse chemicals and residuals accumulated inside the fuel cell stack during operation. Fuel cell purging can be confirmed by the high flow indicated on the reactant flow indicator at the bottom right of the panel. Another indicator of FC purging is the fuel pH monitor located in the center of the panel. DPH should never exceed 1.5 for normal fuel cell operations. As the DPH rises, fuel cell performance is seriously affected and more reactants will be used to produce power until eventually the chain reaction will collapse. Because a small reactant flow rate will not clean any of the residuals and impurities inside the fuel cell, running the fuel cell at idle load will need a purge at smaller intervals than running a fuel cell at normal power loads. The resulting water from the fuel cell chemical reaction will run to an H2O waste tank. Pressure in this tank can be monitored by the H2O waste tank indicator. The H2O OVP vent should always be set to on during an FC purge sequence to prevent damage from overpressurizing the tank, or to prevent water from the tank running back up the piping to the fuel cell where it can then kill the chemical reaction. The last row of switches control battery reloading from the power supply either by FC1 or FC2. Note that CBBT load or circuit breaker must be in the push close position for loading to occur. The talkback indicator will show bar pull if power is being sent to the battery. Electrical power distribution and control. Electrical power inside the ship is provided through two main direct current buses, DC1 and DC2, and one main alternate current bus, AC1. While most essential backup equipment is connected to DC1, it is possible to route power to these equipments through using the backup DC2 in case of a problem with DC1. AC power through AC1 is needed for radar antennas operation and radar antennas pitch and yaw motors. The three power routing switches are used to direct DC and AC loads to respective fuel cells or battery. From right to left, setting whether DC1 bus is linked to FC1 down, the battery, middle, or FC2 up. DC2 bus is linked to FC1, the battery, or FC2, or the AC1 bus is linked to DC1 bus or directly to the battery. Or to DC2 bus. Sorry, it kind of ran off the page. Note that the AC1 bus cannot be tied directly to a fuel cell, as power must be converted by a static converter into AC current. These static converters exist only for DC1, DC2, and battery. Amperage and volts of these respective buses, battery, and fuel cells can be monitored by indicators just above these switches. Once linked to a power source, the respective DC and AC buses need to be remounted, turned on, for them to provide power. The respective circuit breakers need to be positioned in the push closed position, and the respective bus SNS trip switch must be brought to the momentary reset or test position. If there is a problem with the bus, pressing this switch will cause an automatic disconnect from the bus from the power source, indicated by the respective circuit breaker popping back into the open position. Circuit breaker indicators are located in the panel. If the voltage and amperage in the upper right part of the panel. If the voltage and amperage are within operating limits, the circuit break indicator will remain in the pushed position and power will be routed through that respective bus. Pressing the same switch to its momentary trip position will automatically trip the respective bus. Note, a bus should never be set to the trip position under normal circumstances if connected to a fuel cell load, much like an electrical instrument should not be instantly unplugged. Rather, that bus should be switched to battery or a non-started fuel cell and wait for the auto trip to automatically and safely shut down the respective bus. A second row of switches, auto trip, is set to on and will automatically trip the respective bus if an out-of-limit situation occurs, such as low or high voltage, preventing equipment damage. The auto trip set switch must be set in its on position during a bus restart to ensure a safe auto shutdown of the bus. Caution and warning. Caution and warning displays on the electrical panel are located on the lower left side. They presented the crew with non-critical out-of-limit situations, making it easier to identify a problem. The respective CW will trigger under the following circumstances. BAT, battery load, less than 10 kilowatt hours left in the battery, or battery overcharged. DCV, direct current voltage. One of the main DC buses, DC1 or DC2, has a voltage higher than 30 volts or lower than 27 volts. ACV, alternative current voltage. The main AC bus, AC1, has a voltage that exceeds 38 volts or lower than 35 volts. AC over OVC, AC bus overload, more than 100 amperes of load on AC1. H2 pressure, O2 pressure. Cryogenic pressure is less than 200 kPa. FC temp. FC1 or 2 temp stack is larger than 350 Kelvin. FC1 load. Fuel cell 1 load. Fuel cell 1 is either overloaded, greater than 200 amps, or underloaded, less than 20 amps. Fuel cell flow. Reactant flow inside of fuel cell 1 or fuel cell 2 is larger than the nominal 7.5 kilograms an hour. Here we have checklists, which I will not go over. And how long have I been going? Oh goodness. Yeah. I should stop this, and I will continue in the next video. See you then.